I want to do is present a few different strategies. And again, these are things that we have observed as we've solved some of these equations already. But I wanted to have them all here together formally. And just kind of put them all together here. So some strategies for solving exponential equations. First of all, if you've got exponentials on both sides, this is the easy case, but it's also easy to overlook. If there are exponentials on both sides of your equation that have the same bases, then the exponents have to be equal. All right? E to the 2x equals e to the x squared minus 8. Okay? The only way you're going to raise e to two different powers and get the same value is if those powers are equal. Okay? So at this point, what do we know? Very good. 2x equals x squared minus 8. And then that's just a simple quadratic equation that you guys know how to solve. Okay? You'd get it equal to 0 from there. You would factor, or use the quadratic formula if you really like that, or complete the square if you just really like to punish yourself. And you'd get 4 or negative 2. There's actually two possibilities here. Okay? So that's the first strategy here is look out for cases where you have the same base on both sides of an equation. Okay. Another case is when we have only one exponential in the equation. Now sometimes that one exponential is already by itself on one side and all we have to do is take a log here. But even if it's not already by itself, if there's only one exponential, we need to get it by itself on one side and then use the inverse operation. And what's the inverse operation of an exponential? It's the logarithm that has the same base. Okay, so we're looking at, for example, a case like this. 5 plus 6 to the 5x power equals 1,301. So, before we do anything, we want to get the exponential portion of this by itself. So obviously we subtract 5. 1,296 equals 6 to the 5x power. Okay? Now that the exponential is by itself, what are we going to do?
Log 6.
Log base 6. Good. Log base 6, 6 to the 5x. Log base 6 of 1296. Okay. And this is just 5x. And someone with a calculator can find for us the log base 6 of 1296. This is where you might have to use the change of base formula if you don't have a calculator that can do that base.
4.
It turns out to be 4. 6 to the 4th power is 1296. Okay? So that means x has to equal 4/5. Okay? Yes. Do the log base 6 of 1296. So our change of base formula, remember, says that we can use whatever base we want and make this, I'll use the base of 10 because our calculator can do it, the log of 1296 over the log of 6. And again, if you learned a slightly different strategy for solving this, once you get to the point where you're at 6 to the 5x equals 1296, you're welcome to use it, okay? Do whatever you know how to do. The last case is kind of an interesting one, and there's actually two ways you could handle it, okay? One way is easier, but it'll only work certain times. At least it'll only work easily at certain times, okay? And that is the case where we have exponentials, we have multiple exponentials, but we have different bases, okay? So here we have 2 to the 4x power equals 8 to the x plus 4 power, okay? Now, if you see a case like this where, hey, 8 is actually a power of 2, and you could easily express 8 in terms of a base of 2, then you can try to get them both in terms of the same base. All right? So for example, I'd leave this as 2 to the 4x, and I'd write this as 8 is 2 to the 3rd power, and then that's to the x plus 4 power. And what do you do when you're raising a power to a power? You multiply the exponents. So we would have 2 to the 4x equals 2 to the 3x plus 12. Okay? Then we're back to case number 1. We have two exponentials, but the bases are the same, so the exponents are the same. Okay? So 4x would then equal 3x plus 12, and of course that means x would equal 12. Okay? Now, that's obviously not always going to work. If you had 2 to the 4x equal to, 1.75 to the x plus 4 power, you can have fun trying to get those in the same base, but that's where using a second strategy would be easier. The second option, if we can't get them in terms of the same base, just take the log of both sides. Now let's look at what we mean when we're going to do this. I'm just talking about the log base 10. So the log of 2 to the 4x equals the log of 8 to the x plus 4. And now that they're in logs, what can I do with the exponents? Pull them out to the front. So check this out. I've got 4x times the log of 2. And guess what? Log of 2 is just a number. I can plug it into my calculator. Okay? Likewise over here, I have x plus 4 times the log of 8. And again, that's just a number. I can plug that into my calculator. Okay? So, now that I have that, this is a simple linear equation. I've got to punch some stuff into my calculator, but it's not hard to handle. Okay? And in fact, I could go ahead and, if I divide both sides by log of 8, at this point, just to keep this from getting too messy, divide by log of 8. This, if I remember correctly, would come out to x plus 4 equals 1 1/3 x. Is that right? 4 times the log of 2 divided by log of 8. Did that come out right?
Yes.
All right. Okay. So then I subtract x. I've got 1/3 x equals 4, and that means x equals 12 again. You get the same answer either way, but sometimes you'll have to use this strategy here to get there. Okay? Yes?
Will it always be easier to divide one log to the other side?
I only did it so that I wouldn't have to like round and then have error there. I did it so that I knew it was going to come out nicely, but even if it doesn't come out nicely, at least you just have that one number in your calculator that's not rounded, and you can just leave it there and work with it. Yeah, anytime you're solving equations or anything like that, you shouldn't be rounding anything until you get to your final answer. Okay? So don't punch in a log of 8 and round it to 2 decimals or something, and then use that for the rest of the problem. Okay? If you want to write it down as just 2 decimals, but you still have the whole thing in your calculator, that's fine. Okay? But don't actually round anything in the problem until you get to the final answer. Yes. Sure. Alright, so let's think about this one here. This is kind of an application of what we've been talking about here. 525 over 1 plus e to the negative x equals 275. We only have one exponential, so what should our goal be?
Get it by itself.
Get it by itself, alright? First thing, we've got to get it out of the denominator. There's a couple of ways we could do that. Then, get it by itself, okay? So, what do you guys propose we do? Multiply to the other side, okay? So, 525 is going to equal 275 times 1 plus e to the negative x. Alright, divide by 275. That's going to be 25 over 11 equals 1 plus e to the negative x. These are both multiples of 25, so... Alright, subtract 1. Now we have 14 elevenths equals e to the negative x. And now, look, we are going to take the natural log because at this point, our exponential is by itself. Okay? Don't take a log at all until you've got the exponential by itself. And then you're right, we're going to take the natural log of both sides. And that's going to give us negative x equal to whatever this is. Alright? So therefore, positive x would be negative, whatever that is. Negative 0.2411 or?
Negative 0.24.
Okay.
If you're rounding to 10 thousandths.
Alright, so negative 0.2411. Okay. Any questions about our strategies here for exponentials? Okay, now for logarithms, there are 3 kind of cases that we want to look at as well. Alright, again we have the case where we have them on both sides of the equations but the bases are the same. And just like our exponentials, if logarithms on both sides of the equation have the same bases, then the arguments of those logarithms are equal. So here we have a log base 9 on both sides, so we know what?
Plus x equals 2x minus 1.
Come on guys, wake up. What do we know?
4 plus x.
There we go. Alright, it's really, really easy, but it's also easy to overlook. Okay? So 4 plus x equals 2x minus 1, so obviously then x would equal 5. That's a pre-algebra equation at that point. Okay? So that's our first case. Second case, if the logarithm's only on one side, again, we're going to use the inverse operation and write it as an exponential. Notice how these two parallel what we just said about exponentials. Okay? If it's only on one side, use the inverse operation. Rewrite it as an exponential with the same base. So we could rewrite this equation, log base 10 of x squared equals 6, as what?
10 to the 6th equals x squared.
Okay, 10 to the 6th. 10 is the base, 6 is the exponent. That will give us x squared. And that means that x equals,
1,000.
yeah, 10 to the 3rd, which is 1,000. Okay. Now, are there other things that you could do? Sure. Could we have taken this 2 out in front, make it 2 log of x, and then divide both sides by 2, so log of x equals 3? Yeah, but then we would need to write it as an exponential, and it would have given us x. Okay? So, either way, you get the same thing. The last one that's a little bit more complex is here. If we have multiple logarithms, this is where what we were just doing in the last section really comes into play. If there's multiple logarithms, we have to use the properties for logarithms to write it as a single logarithm. Okay? So, in this case, we would first want to get the logarithms on the same side of the equation. Okay? So if I subtract here, ln of 2x plus 1 minus ln of x equals 3, I can't write it as an exponential yet because I have more than one log. So what am I going to write this as?
2x plus 1 over x.
Divided by x.
There we go. 1 natural log 2x plus 1 over x. So what does this mean?
E to the 3rd equals 2x plus 1 over x.
Yeah, our base is e, so e to the 3rd is 2x plus 1 over x. Now, believe it or not, this still isn't too bad, okay? We know x can't be 0 because of our domain. We know x has to be actually greater than 0 because of this. Okay? We're in a logarithm. The domain is x has to be greater than 0. Alright? So, if I multiply here then, we have x times e to the 3rd is 2x plus 1. I would need to, at this point, get this into my calculator so I know the decimal. Alright? What is it?
20.0855.
20 point what?
0.855.
0.86.
Okay? So, that's how many x's I have on the right. That equals 2x plus 1. So I need to subtract 2x, 18.0855. So x is 1 over 18.0855. 0.055.
Roughly.
Okay? So, doesn't turn out very nicely in this case, but that's okay. The strategy would be the same though. You get it down to one logarithm, then write it in its exponential form. Are there any questions about the strategies? A lot of this is made up of observations that we had made along the way, but now it's all in one place. Yeah, Caitlin?
For the last one where it says 2x plus 1, is that x times e to the 3rd or x minus?
Oh, right here?
Yeah.
That's x times, because what we did right here, to get the x out of the denominator, I multiplied on both sides.
Okay.
Anything else? Okay. Now, what I would like you to do for tomorrow, we'll start by taking questions on these, but you'll notice the practice I gave you is all just equations. Starting a little basic, moving on to more complex. Okay, those are exponentials. Here, it's just the odds on these. So you've got 6 logarithmic equations to solve. You've got 6 exponential equations to solve, so 12 problems for tomorrow. Not too bad. Then when we get to class tomorrow, we'll take any questions that come up from that. There's one more element that I want to consider when we're dealing with logarithms. And then the remainder of our time for the fusion period is going to be small group work and really just hammering away at these and hammering away at applications of these so that we can get really comfortable solving them. Okay? So